All right, everyone, welcome to homework 4.3. I'm doing this a little bit differently today because I forgot my pen at work. So, let's go ahead and take a look down at tonight's homework. So today we looked a little bit more at quadratic functions, and again, I'm just going to reiterate that a quadratic function has some kind of term to the second power. And that helps us to determine that it is a quadratic function. So let's take a look at the starting one. So it says sketch or describe the figure in step 4 and step 15. Remember, we're looking at finding some kind of squared pattern here. Now notice that even though this square is written up here, there's still 4 here, and same thing here, this could go here, and then there's 9 here. For step 1, it's 1. So the pattern here is 2 by 2, 3 by 3, 1 by 1, which simply means that the pattern here is that we are squaring the number of steps, right, the step number. So if we were to look at the 4th step, then we would do a 4 by 4 minus that one little corner, right? So like this. So now there's 16 minus 1, so 15, but then that plus 1 of 16, so still 4 by 4, right? So in step 4, we would still have 16, and then in step 15, we would have 15 times 15. So you may already recognize that to be 225, but you can also use your calculator if you need to. Write an equation to represent the relationship between the step number n and the number of small squares y. So y equals n squared. Explain how your equation relates to the pattern. So n is the step number, and we have a square of side n, right? So each side length is n based on the step number. It says, which expression represents the relationship between the step number n and the total number of small squares in the pattern here? Okay, so here now we have what would be 2 by 2, except we're missing 1 here. We would have what would be 3 by 3, except we've subtracted 1 from here. So you can see that we have 4 minus 1, 9 minus 1. Here would be 1 minus 1, which is 0, right? That's why there's no little square there. And so the best reflection of this would be b, n squared minus 1. Now, if you weren't sure, you could always plug in the step numbers to see what you get, and it should work out. So if you plug in 1 here, 1 minus 1 is 0, that works for this. 2 times 2 is 4, minus 1 is 3, that works here. And then 3 times 3 is 9, minus 1 is 8, which shows that that works here. If you were to plug in the step number for any of these other equations, it would not work out to be the number of squares here. All right, number 3 says each figure is composed of large squares and small squares. The side length of the large square is x. So this whole length here is x. Write an expression for the shaded, the area of the shaded part of each figure. So for this one, the area would be x squared minus 1, 2, 3, 4. Here we would have x times x plus another x times x. So this would be 2x squared plus, we have 2 times 2 is 4, 2 times 2 is 4, 4 plus 4 is 8. You could also think of this as 2 times 4 here, which would still give you 8. The key thing is that you have 2 larger rectangles here, and you need to add them together, so that would be 2x squared. You could think of this as x squared plus x squared, and then 4 and 4. So 2x squared plus 8. Number 4, here are some pairs of positive numbers whose difference is 5. Find the product of each pair of numbers, then plot some points to show the relationship. So 6 minus 1 gives us 5. That's the difference, right? But 1 times 6 gives us 6. 2 times 7 gives us 14. 3 times 8 gives us 24. 5 times 10 gives us 50. And 7 times 12 gives us 84. So let's go ahead and plot those points now. 1, comma 6 would be about here. 2, comma 7, a little bit higher. 3, comma 8. We skipped to 5, comma 10. And then we skipped to 7, comma 12. Okay, but here we can see what looks like is starting to potentially form maybe a line or maybe a curve. Now we can tell here though that when we increase here, we're adding 8, then we're adding 10, then we're adding 26, right? So we're not increasing by the same amount. We're also not multiplying by the same amount each time. So we know that this is both not linear, right? We can tell it's definitely not linear. And then if we want to go ahead and see if it could be exponential, then we could divide 14 divided by 6 gives us 2.3. Oops. 24 divided by 14 gives us 1.7. 50 divided by 24 gives us 2.08. So we're kind of like all over the place here. And then 84 divided by 50 gives us 1.68. So the factors are also not the same, showing that this is likely not exponential, the first number and the product. Now it says, is the relationship between the first number and the product exponential? And so we're going to say no, because the factor is different. Now actually something that I didn't also show you here is that the in between here would be 4, right? And so 4 and the difference with a difference of 5 would be 9, right? And 4 times 9 would be 36. So if we were to do 36 divided by 24, we would get 1.5. Again, not the same anyway. And then here we would get, if we were to talk about 6, we would have 6 and 11, and that's 66. So 66 divided by 50 gives us 1.32. So either way, the factor is not the same. All right, number 5 says, here are some lengths and widths of a rectangle whose perimeter is 20 meters. Complete the table. What do you notice about the areas? All right, so we have a rectangle. The perimeter is 20, which means just the length and the width has to equal 10. So you can see that here, 1 plus 9 equals 10. And then 1 times 9 gives us 9, so that's our area. 3 times 7 is 21. 5 times 5 is 25. 7 times 3 is 21. And then 9 times 1 is 9. Without calculating, predict whether the area of the rectangle will be greater or less than 25 square meters if the length is 5.25 meters. So if it's 25 square meters for 5 times 5, then a rectangle with a length of 5.25 would have another side or width of 4.75. When we multiply those together, we will get a smaller number than 25. So I'm going to say less because the width would be less than 5, and 5 times 5 equals 25 gives us the greatest possible area. All right. Letter C says, on the coordinate plane, plot the points for the length and area from your table. Do the values change in a linear way? Do they change in an exponential way? So again, we're doing length and area. So for a length of 1, we have 9. For a length of 3, we have 21. For a length of 5, we have 25. For a length of 7, we have 21. And for a length of 9, we have, again, 9. So we can see, no, it forms a parabola, and it changes both increasing and decreasing, which linear functions and exponential functions do not. It's also, the increase is different, and the factor is different. All right, let's look at our pattern of dots. So complete the table. So for step 0, we have 1. Step 1, we have 2. Step 3, we have 5. Step 3, we have 10. How many dots will be there in step 10? Well, we can see here, let's look for the square pattern. Here we have 3 by 3, 2 by 2, and we're adding 1 here. Let's see if it works here. Well, here's 1, and then we're adding 1. And then here we have just 1. So the pattern that I'm looking at is likely going to be n squared plus 1. So in 10, we would have 101 dots. Step n, as I said, is n squared plus 1. All right, my last two problems are review problems. Mai has a jar of quarters and dimes. She takes at least 10 coins out of the jar and has less than $2. So this is a inequality situation. And it's practicing the inequalities that we are going to consider. So we're considering dimes and quarters, right? So we're considering 0.25x plus 0.10y, right? Quarters and a number of dimes. And then that is going to be less than $2. The number of coins that we have are 10. So x plus y equals 10. A number of dimes and a number of quarters is going to equal 10. All right, so this is the system of inequalities. Oh, and I'm sorry, I said equal to, but she says takes at least 10. So she takes greater than or equal to 10 coins out of the jar. It says, is it possible that Mai has each one of the following combinations of coins? If so, explain or show how you know. If not, state which constraint, the amount of money, or the number of coins it does not meet. There's a couple ways we can do this. 1, we can graph these. 2, I can plug them in and see if they work. So 3 and 12 is greater than 10, so that works. We need to decide, though, if it is less than $2. So 3 quarters would be 0.25 times 3, plus, then we have 12 dimes, so 12 times 0.1. That gives me $1.95. That is less than $2, so this would work. Okay, let's try 4 quarters. 4 times 0.25 plus 10 times point you might recognize as $1 already. That is exactly 2, so no, because it says less than 2. And let's try the last one. 2 times 0.5, 50 cents. Oh, sorry, no, I calculated those 2 times 0.25 plus 5 times is 50 cents. Oh, 5 times 0.1 is 1. That is less than, so this one would work. Okay, so you can plug those in and show that they work. Or again, we could also graph these. I can put this in graph form to see what would happen with that if I solve for y. So I'll go over that in a second after I finish this next one, in case you wanted to see how I did that. All right, number 8, a stadium can seat 63,026 people. For each game, the amount of money that an organization brings in through ticket sales is a function of number of people, n, in attendance. So f of n gives us the amount of money. If each ticket costs $30, find the domain and range of this function. So we would have money, right, times n. So let's say dollars times n gives us how much money we can bring in through the ticket sales. All right. So at maximum, then the ticket range is $30 times the number of people that can fit in there. So if we want to think about the range, how much money we can make we can make anywhere from $0 if no one attends to, so this is for our range or our Y values, which are our outputs, how much money we could make, all the way up to 63,026 times $30, all the way up to 1,890,780. And then for our X values, our inputs can be anywhere from 0 people to 63,026 people. So this is really just a review to see that you know what your domain and range is. The other thing is each ticket costs $30. So these would be in increments of 30. And each person can only be a whole person. So in whole numbers or positive integers. All right. So I said that I would go back to this part. I'm going to go back to this part real quick just to show you how we could graph this. So if I wanted to graph this, I would need to solve for y. So I would make this, I would subtract the 0.25x from both sides. So we would end up with 0.10y is less than negative 0.25x plus 2. And then I need to divide by 0.1. Right, and so when we do that, we would get y is less than negative 0.25 divided by, not negative, sorry, 25 divided by 0.1 gives us negative 2.5. So y is negative 2.5 x minus plus 2 divided by 0.1 should be 20. Okay, so that's one of our equations. The other equation would be x and y here. We subtract y is greater than or equal to negative x plus 10. So I can graph those equations. Now you know how to graph them by hand using the slope and the y-intercept. The y-intercept there is, I forgot the x, that's important, is 20. So it's going to start at 20. And notice it's going down, right? And then here, this would be negative x plus 10. Now, I do also want to name that, this is a review of how to use your calculator, we can go over here to this part and I can change what kind of line I'm looking at. So I said less than, so I should have a lower triangle. And then same thing here, this is going to be a less than situation. Which is the lower triangle. So they should both end up with a, oh, I'm sorry, actually the other one, this one is a greater than or equal to, so let's change that. Oops. No, I didn't, no, that's not what I wanted to do. Okay. There we go. Okay, magenta's fine then. All right, and then I can go ahead and graph that. So now these double shaded areas are the areas that, right, this area up in here, that I could say are solutions to the equation, right? So if you can look and say, well, 3/4 and 12 dimes would be up here in the shaded area, that would work. 4/4 and 10 dimes, 4/4 and 10 dimes would be too far up there, it would be above. And then 2/4 and 5 dimes, make sure I made my thing correct here. It's less than $2. X is the quarters. Yep, so 2/4 and 5 dimes. Let's go ahead and make sure that I did this correctly. Yes. Oh, I see what I did. So, come on, y'all. Okay. Number 3, hopefully you caught this on Miss Lee, is not an option because while it does fulfill the second constraint, So I was like, it's not on the graph, right? Look here. And that's how I caught myself. 2/4 and 5 dimes would be here. That's in the blue shaded zone, but not in the blue and pink shaded zone. And the reason is because 2/4 and 5 dimes is not greater than 10 total coins. It's only 7 coins. So the only possible answer is number 1. Ooh, watch all the way through. Okay, now I did promise that I would go back and look at the classwork here for you. So let's go back to the classwork. In the meantime, if you need it, the code word for today is carnation. The code word for today, again, is carnation. It's a type of flower, in case you're not sure how to spell that. So go ahead and go back and look, put that as your code word. I'm also now going to go through the classwork, particularly the perimeter part, because it seemed like people had trouble with that. So in order to do this perimeter part, we're going to go back to this part right here. And it's asking you to find a relationship between the step number and the perimeter. So let's make a table. Step 1, step 2, step 3. And then the perimeter here is going to be, remember the perimeter is side lengths added up. Now for a square, that's 4 times whatever the side length is, right? So here, if each one is 1, that's 4. A perimeter of 4. This is a perimeter of 4, perimeter of 4, perimeter of 4, perimeter of 4. Right? So for 1, step 1, our perimeter is going to be 16. 20. 5 times 4. Because if we add up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now the perimeter for number 2 is going to again be these 4, which means 4 times 4 is 16. So 16 plus, this is a perimeter of 2, and then 2 times 4 sides is 8. So this is going to be 24. Here again, we have a perimeter of 16 again. So that's our starting perimeter, right? And then we have a side lengths of 3. Remember, we're not counting the inside squares, we're just counting the side lengths. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So plus 12 is going to give me 28. Well, you should be able to recognize that here we're increasing by plus 4 each time. All right, and so that means that this is a linear function because it's increasing by 4 each time. And to find the equation here, remember, because I'm adding 4 each time, that's repeated addition, which is multiplication. So 4n. And then to find the rest of the perimeter, each time we had this 16 on the outside of these little squares, right? That perimeter there. And that is our starting value, or our y-intercept. You could also see that if you were to look for the 0th term here, that it's 16. So 4n plus 16 equals p, the perimeter. It says for the step pattern you created in part 3 of the activity, write an equation to represent the step number and the perimeter. So here in number 3, if we're creating this pattern here, we're doing, let's say 1, 2, 3. So 1 would be 1 times itself is 1 minus 1 is 0. So you would end up not having any squares there. But for number 2, 2 times 2 is 4. But then minus that 1 would leave an empty space here. Okay? So 3 by 3 be an empty space up here in the, I guess I can't do that. Sure. An empty space up here in this corner here, right? And so perimeter-wise, we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And so here, right, we would have, I said, for step 2, it's 8. For step 3, it's 12. We are again increasing by 4 here, but the starting amount would have to be different. So, unlike the last one. So our starting amount, if we go back 1, would be technically 4 sides here, and step 0 would be 0 sides here. So what we can see here, though, is that we are going up by 4s each time, and then this means that our starting amount is 0. So our best equation for this would be P equals 4n. Now, honestly, I don't love this question because really for step 1, we don't have any squares, so we don't have a perimeter. So it's not entirely accurate, but the one that best represents that would be 4n. Okay. Erase that. Okay. And then are these linear functions? Yes. We have a coefficient of n, and it is increasing at a constant rate. All right. Growing steps. Sketch the next step in the pattern. So, step 4. I strongly suggest when you look at these patterns to look at what is the square for the step. So this is the square here, this is the square here, right? And we want to look at what is happening next. So following this pattern, we would have a step of, that's not super even, but we'd have a step of 4 by 4s. And then an additional, here we have 2 additional stacks. So we'd have 2 additional stacks, 2 additional rows on top of this original square here of 4 by 4, plus then another 8. So there's my sketch. Kieran says the pattern is growing linearly because the step goes up by 1. The number of rows in the columns also increased by 1. Well, no, I don't agree because that's not the number of squares we're adding. So here we're adding 2 squares, right, to go from 2 to 4. Here we are going up an additional 1, 2, 3, 4, 5, 6. We're adding an additional total, actually, sorry, not 2 squares, because total we start at 3, then we have 8, so we're going up plus 5, and then here we have 9, 10, 11, 12, 13, 14, 15, so going from 8 to 15 is plus 7. So we're not increasing by the same, not increasing number of squares by the same amount. Diego and Jada write 2 equations for this, n times n plus 2 or n squared plus 2n. Are either Diego or Jada correct? Show your reasoning. So I do want to note here that n times n plus 2 equals n squared plus 2n. So these are actually the same equations. So 1, they're the same equation. They're just written different way. They're equivalent. And then 2, does it represent the situation? So if we plug in 1, we would get 1 plus 2 is 3, and we do have 3 squares in this first step. We would get 2 times 2, 2 squared is 4, plus 4 is 8, we do. And the reason is because, and I'll show you an example here, here we have n times n plus how much here, right? So we have n squared plus we have an additional n, right, that we're multiplying by. And then we're doing that twice, right? So this, because there's 2 stacks there, all right? So if we were to think about multiplying out the whole thing, it would be n times n plus 2. That's where Diego gets this equation. And so we get n squared plus 2n. Okay? If we were to think of them as 2 separate cubes, we might think of them as n squared plus, doing this here is n times 2. Right? So both of them figured out a way to represent that in different ways. But so these both work. And again, you can explain by showing me on the drawing or explaining that if we were to plug in 3 squared plus 2 times 3, we do in fact get that number of squares. We get 9 plus 6 is 15. All right. That's it. If you have any questions, feel free to reach out. Happy homeworking, and I will see you tomorrow.